I'm very happy to be here.
The first topic is going to be about the material. So we've been talking about a lot of different things this week in terms of what constitutes nanocarbon in space. So we have a few questions about that. The questions here are, so we've talked about various forms of nanocarbon materials. There's a lot of different types, and I think one of the questions is what should we focus on first? I mean, ideally we want to understand everything, but which of these materials are the most important, promising, interesting areas to consider and study? And then the final question here is like, what are the most pressing needs in terms of figuring out those nanomaterials? So let's maybe start from my right. So Ali, what would you say is the most important, promising, or interesting nanomaterials to consider and study?
Well, I would say pass, because I'm a PA person. I think now with the new JWST observation, we are opening a new windows. We have so much spectral resolution that we can start figuring out the small details there. So I think we need to go back and see what we have learned so far in this time where we've been waiting for this observation, and see what other steps we can take further.
Okay, so the answer is pass with a focus on stability of the species.
Yeah.
Okay, great. Hassan.
On the same question, I will join also, Annie, because I did all my studies on pH, and I think they are important. However, we still have a big problem about the hypothesis of pH. In a way to confirm, basically, the hypothesis of pH, especially now with the detection of small aromatic rings in the interstellar cloud, with a discussion with the people like José Cernichao who detected these molecules. The question was, are you able, at least with the instrument of today, to be able to detect the largest one with or without CN connection, and to understand what is the population in the interstellar cloud that give birth basically to the planetary system or whatever asteroids where we discover PAHs?
I think looking back at all the presentations and the joint projects, etc., and what people have been up to today in the computational side, we have enough material to share to build a block of data to be shared and to be used in predicting the infrared spectra more accurately, and to exploit them in the current observations.
A long time in our history, the only pure carbon we know of are graphite and diamond. And then, of course, later we learn about fullerene. Now, I want to tell a little story about the origin of fullerene, because I work in Hertzberg's group in the 1970s. And Harry Kroto came to our Hertzberg's lab every summer. And we were observing cyanopolyon, a long-chain molecule which can be, the rotational lines can be detected at the centimeter wavelengths. And Kroto wants to predict the transition frequencies for higher order cyanopolyons. And that led to his later discovery that of the laboratory synthesis of a new form of carbon, which is fullerene. Citing this example, new advances in chemistry can actually be an intentional result of astronomy. Now, the hydrogen is the most common element in the universe, and carbon can easily react with hydrogen in many ways. The most natural product of combustion is amorphous hydrocarbons, and these can have many different structures. And as we discussed, pH is only one of the very small fraction of that structure. The artificial synthesis of this kind of amorphous hydrocarbons would lead us to know of a new kinds of material which may have implications in astronomy, understanding the mystery of unexplained spectral phenomena.
Comments from the audience? Ewan, yes.
So I think one of the issues with these unidentified infrared bands is that C60 is the unique case, right? Because of its high Cauchy symmetry, you have these 4 bands. So that seems to me the obvious one to target different environments and see if you can get observational data, high quality, that are free from observational constraints. Seems to be a good thing to do. The other thing is these relatively small pH type structures, these cyano, naphthalene and benzonitrile and so on. It's a question, is it worthwhile trying to find see what the sort of upper limits to their coal densities would be in different regions, given that they have been detected in cold dark clouds.
Bars are difficult. So well, let's maybe be more general. Actually, let's just talk about these unidentified infrared emission bands or the aromatic infrared bands. So even within the PA community, there's people that very much disagree about the nature of this emission, right? So some people say like, well, it's a small number of very stable molecules. There's others say like, no, it's a mixture of hundreds or thousands of species. You can actually show with the database, as soon as you add something like 30 individual species, you always get like a similar average emission spectra. And so already within the PA community, it's not quite clear which of the two it is, and that has major implications for how you actually study these bands and what you can infer from them.
In the 1960s, I was at Minnesota when the UIE bands were discovered, and when Roger Neck and Walter Dooley proposed that they are due to organics, no one believed them. It's only in the 70s when more and more molecules were discovered by rotational transitions, people began to accept that there could be organic molecules in space, and PAH happened to be the simplest organic molecule, and that became the very popular theory. So we have a natural resistance to accept things which are more complicated than we used to believe.
Yeah, but I think for PAH is kind of what the PA community will mostly agree upon is that the emission originates from largely aromatic species that are not like 1,000 carbon atoms. They're in the tens to maybe hundreds carbon atom range, with small fraction of aliphatic bands, and other than that, yeah, I mean it's a bit out there, I would say. But you would.
In terms of experiments, I mean, would it be useful to try and simulate the sort of interstellar radiation field more accurately and look at the floating products of large, mostly aromatic structures?
In my group with Christine, we did a lot of study on PAHs with whatever UV lamp. Some of these data are not published, but we have extremely very similar results than what Alessandra was presenting yesterday, that you lose hydrogen for the larger one, and after that you generate carbon cluster. Once these molecules absorb, I would say, the efficient or the enough energy to break, they will break in the same way. Even though you do collision-induced dissociation sometimes, you will get to the same fragmentation product. There have been also some measurement on the synchrotron with the UV tuning stuff to see how much you can produce fragment or you can doubly ionize these molecules. So there has been a lot of study on this, and people are continuing working on this. But to do it in the lab, it's much more easier than taking your system to the synchrotron, getting like 2-3 days. And it's actually a very nice idea because you can break it in the lab, make it benchmark, and get to whatever you...
We really needed the results from the lab and go back and try to understand, how this molecule can survive. Do they break down? What kind of mechanisms are happening that are not like photodissociation or irradiation? Until, I don't know, less than 10 years ago, nobody thought about isomerization for these species, but now we see that we cannot explain what we see in the lab.
But I think that we should start looking in 3D species, not on the 2D.
Yeah, but the problem with the 3D PAs, let's say, is that there are few that have been synthesized. So, this coranulin and sumanin, but it's there. So we really need the help from the synthetic chemistry department to find, new route to create these molecules.
Actually, most people assume that pHs are planar, but if you actually do the optimization of the geometries for most of the neutral pHs, they're actually non-planar. So.
And also clusters, that's naturally 3D material, and we have been thinking that they are responsible for some of the features out there. I know that Christine group has been studying them both from a theoretical and an experimental point of view. So I think that's also another way to go.
I just want to point out something not about the breakthrough in experimental setups that you can build. Simulating this PAH infrared or whatever dissociation pattern is not easy, but it's accessible. Working for some people that never worked with PAH, these these species are very condensable. So when you put them in the gas phase in your vacuum reactor, it's very complicated to deal with them. So sometimes from experimental point of view, working on this PAH spectroscopically or fragmentation or kinetically working, it's very complicated, which makes sometimes the results coming out from this research not a lot, actually.
Yeah, try to ask to people that work with ice, for example, that you want to put PAS in ice or fullerenes. They don't want to mess up their setup with oily things that they cannot remove.
Chris.
Do you think there are other fundamental structure types that we could be looking for, like tubes or seams or these other structures? Or should our focus be more on structural variants that are existing on things like fragmentation species still usually existing? I mean, is there another holy grail out there somewhere that we haven't thought of yet?
Basically, if you take a PAH and remove a lot of hydrogen from it, let's say C16H10, and you remove, 4 or 5, 6, you end up with something like a carbon cluster with hydrogen. I don't know if people synthesize that chemically, like whatever, like you synthesize any product, but I think people should look at these things where we say it's dehydrogenated PAHs, because they have sometimes these curved structures that we are talking about. So it's in between PAHs and fullerenes. It's something in between, but people don't synthetically chemistry, but in suit we see them a lot, actually. So this could be a nice candidate to look for as a spectroscopy candidate. However, how you can generate them in gas phase, it's another story.
Do you have any idea about the structure of these species?
That's a good question, because the carbon cluster, we say, for example, let's say at C equal 10, you get this linear one, and when you grew up from C10 to C30, you start curving them. I think they are very similar. We see them in the photofragmentation procedure, for example, of pyrene, coronine, or whatever, where you have this shape of aromatic cycle will change, but I don't think there is a lot of study on the structure of these things.
I think that in Toulouse, but in the theoretical department, there was a study about what kind of shape you have when you have just carbon cluster, and they come up with this, a bicycle, ring, or pretzel-like structures. These are, they look really nice. It would be interesting to see how resilient they are. And they did also some spectroscopic studies. So for sure there's something to go in
I'm sure these things are there. We can't detect them, but the problem is,
And the main problem in the lab is really trapping these species in an ion trap or in whatever gas flow, where you can do spectroscopy to compare that to whatever observation you can see, because they are complicated.
In any event, I think the techniques are getting better, but also, and I think this is very exciting, that in the last 10, 15 years or something, all the laboratory techniques, they have become so much more sensitive. I mean, now you hear people, casually mentioning like, we put like 10,000 molecules in this ion trap and they stay there. Like 10,000 molecules, like that's incredible that you have the sensitivity to measure things in those small numbers. So there's more and more spectra becoming available of relevant species, and people are actually searching for this, are comparing to observations. So we get to the point where we're able to exclude more and more like small families of species. So we're certainly getting there. Martin, last comment.
Keep in mind that in ICES or in other environments, everything is mixed. And everything, it's a combination of molecules and bases. I don't know exactly if we can manage to calculate everything in advance and to understand this is something just a little bit. Yeah.
That's
the exactness to calculate exactly this.
Anyway, I think we should move on to the next question. That's a question about research priorities. And so the question that I asked our panel members to think about, and by all means think about it yourself as well, if you could spend 100% of your time in the next 2 years on researching a specific question with an unlimited budget and a large team of your choosing, what would you be doing and why? Ale.
Well, I think I will going to do what I think it's a priority. So really put together a teams where there are experimentalists. I'm not an experimentalist, but I may hire a postdoc and do experiment on the photostability of PAS. And also high resolution spectroscopy for the infrared side, because we can learn a lot of things about anharmonicity, for example, or if you go to the UV visible, and you can have this very nice high resolution spectroscopy, you can see Erzberg-Teller, I forgot the word, but you can see all the coupling, and this can tell us also a lot about the stability of these species in the interstellar medium. So that's what I'm going to do. You give me the money?
If I would have it, you would get it all.
Great.
Awesome.
So me as an experimentalist guy, I always think that breakthrough in instrument development, such as an observation, let's say, GWST or whatever, you get to the point where you make a breakthrough in analysis. Actually, now we are basically, how we say it, on the analysis of meteorite and other stardust analogs. We are building this machine where we have high mass resolution, and we are trying to go, for example, with a scanning laser down to microns. But ideally, you want to go, for example, for nanometer size desorption, which has not been done. There have been one attempt by Renato Zannubi, one of the godfather also of the L2MS, using AFM tips. So basically, if you have enough money, really enough money, as you said, a limited budget, and really very qualified engineer, which they exist, you would think about a system where you can desorb and ionize at the nano level, so you can combine these analyses from extraterrestrial material with the mineral part, so you can understand the chemistry that happened for this material. But also, ideally, you want to build up a stardust machine, and you go up to 3,000 Kelvin, or at least, which we have been unable to do with the sputtering gas technology, because they wanted that for surface science. You could build up a chemical reactor. It does exist in some cases, but you work on very low vacuum, and you work up with where you can tune your temperature to be able to confirm, for example, the slide where we show the different products that you get. And you combine this analysis technique with the chemical reactor all at the same time, so you reduce any contamination process that you could get from the outside. Here we are talking really about few millions and at least 20 to 30 engineers highly qualified in this, but at least you tackle the real question of formation of these molecules from carbon, hydrogen, C2H2, or whatever other gas that you could have.
Sounds to me like your ERC grant is written.
I think so.
Yeah, my priorities will focus mainly on dust grains compositions, so development of more systematic ways to study those dust grains and investigate the catalysis towards the synthesis of organic molecules.
My own ideal instrument would be a infrared satellite with high spectral resolution. But there is a lot of serendipity in science, and that's why over my careers I always want to push for telescopes which are general purpose and not done for a specific purpose. We have to remember in history, in the late 19th century and early 20th century, you ask a physicist what is the most important problem, and they would say the search for ether. You ask an astronomer, during those years, they would say the search for Vulcan. So those were the priorities at that time. See what happened to them now. So we tend to forget our failures, and a lot of success in science are not planned.
So I've actually also thought about this question, and I know you're all going to think like, oh, he's going to talk about C60 again. No. So if there is one question which has been bothering me enormously in the last, 20 or 25 years, and I've over the years, I've asked a lot of people the very same question. How do you make dust around carbon stars? That, I think, is the fundamental question that we need to figure out. Everything else in terms of molecules and carbonation stuff is based on that. And if you look at a lot of experiments, what you see is like in the combustion experiments, you make these molecules and you make the suit so that you make this dust very quickly, but nobody really understands exactly how. And it's the same if you look at astronomical observations. If you look at carbon stars with low massless rates, you see fairly simple molecules and silicon carbide. In a very short amount of time, as massless rates increase, you just make huge amounts of dust. And it looks like it's amorphous carbon, but a lot of what's happening in the whole dust formation zone is not visible to us, right? So we actually don't know how you make that dust. You don't know what the pathways are. You don't know what the structure is of the dust that results. And that has been bothering me a lot. And to me, it's like a very big question. It's a sort of question where you need like the best experimenters and the best theorists and everybody all working together on this one problem. And then all the spin-offs that you get in that process, I think, answer like half of the questions that we have about nanomaterials in space.
You watch a nova, they form silicate dust in 3 days. You see them form in front of your eyes. But theoretically, you ask a chemist, this is totally impossible. So I don't think it will be anytime soon we can theoretically answer this question, except that nature is a lot smarter than us.
Just a small comment, but exactly what you are saying, it's not a problem of 25 years. I would say it's even more, 50 and 60 years in combustion. You have really dedicated people, even the Sandia National Lab, which is humongous and work on this subject. You always get to the point where you don't understand. Probably it's a question number 3 on your panel, is that how you go from this large molecule to the first particles that nucleate. The nucleation process on itself, it's not something we understand fully and correctly. In the combustion system, they said at the end, you could be having a mix of these 3, van der Waals interaction or chemical polymerization. So if you have difficulty to see that on Earth, I think it will make a long time before we understand really by observation how you could do that in space, I would say. But that's...
Martin?
I believe in principle this process should be somehow similar to information of any dust. I mean, okay, we may have different elements in this process, but generally fundamentally it should be the same. And I would like to draw your attention that atmospheric communities that are more related to the clouds and so on have made like amazing progress in this, like, I don't know, last 15 years. So they are able to pretty well describe the condensation in our atmosphere. And I think the physical understanding of this process is the space more or less similar. And because it's turned out that the initial element of this condensation is sort of a, if I remember correctly, H2S4 or something like that, which is also the very rare in our atmosphere. Then it's like a, I don't know, few of these molecules, it's enough. And then after this passing to this kind of barrier, the process can spontaneous.
But even with like perfect spectra, this is one of those key problems that we've been stumped over. Like, how do you even define where a band starts and where does it end? But we're working on something like that, and it'll come with uncertainties, but it's still going to take a long time until we have the final data together. That's why I have an army of students. But yeah. So.
In a much wider context of here, and I think one of the areas that's really going to change fundamentally is our understanding of amorphous carbons in the next few years, and partly for things like these gap potentials, some of the new machine learning potentials, so we can now model at DFT quality, but with sufficient speed that we can start to do much larger low symmetry systems, and the obvious target is amorphous. And there's really, really interesting stuff going on in Curtin, and there's several labs working on this. I think our idea of amorphous is going to become much more nuanced quite soon. The next 7 is something I'm looking for in the next 2 years. So if I can have your money, I will actually give it to the other guys, and I'll just take a little bit for me to go on holiday for 2 years and come back and see what they've done. But a more broader point on this, maybe, I don't know how relevant it is to what you guys are talking about, but there's a lot of subtlety in what is an amorphous carbon in the kind of in the ground level. Everything tetrahedral amorphous carbons, there's glassy carbons, which are aromatic but feature all the pentagons and reverse curvature, Schwarz-sign type structures. So not everything we're talking about is focusing 0D molecular things. So we're looking at convex surfaces, but there's inverse, there's concave surfaces, which you get on things as well. And it's an interesting chemistry, I submit. I don't.
Yep.
One of the first evidence that CCC can form inside amorphous regulated layers of this regulated amorphous carbons. It's pretty tricky in experiment, but the conditions are very complicated, but they managed to it was an accident, but they found out that they simply lose the formation of CCTV. So perhaps amorphous materials are the way to go around instead of same way.
If you can reach C60 with the destruction or for the processing of such amorphous material in the 90s, Professor Dule and colleagues did some experiments but has laser ablation of hacks, and they found that they could produce a tiny amount of fluorines, but in principle it's possible. And also the last result mentioned by Rancet, and is also interesting. So that would be, if we can understand the full information, I think that we could understand, at least some part of the puzzle, how the carbon is evolving around the neighborhood, for example, the AGB to the PM stages.
Yeah, okay. So, and then, that first question is, of course, very ambitious. How about less ambitious? The last question, what science finding would we like to see at next year's meeting? This is like putting you on the spot, right? What are you going to present next year? And then next year we'll play these movies again, and then, Amorphous carbon. Yes, amorphous carbon.
I was just going to say amorphous carbon, a measure for amorphous carbon. So thank you very much for stealing the show. So the thing is that when I think about amorphous carbon, I have three markers. One of them is the specific surface area, and the second one is the aromaticity. So specific surface area can be calculated by traditional methods, and for the aromaticity, I am strongly hoping that I will be able to scale my code to something relevant for amorphous systems. So we can have a numerical representation. So this has a specific surface area of this much number, aromaticity measure of this much number. So you can have a numeric DNA-like identification for various types of amorphous algorithms. I don't know.
So we have 2 years, about, well, a bit less, I think, left in the cost action. And I think a key thing is, in meetings like these, to get inspired and to inspire, to get new ideas, to learn from each other what sort of issues other people are tackling and dealing with, and how we could help other people's research and how they can affect our research. And so I think I have like two questions, like what sort of actions could or should we consider in the next 2 years to promote more collaborations? There's a lot of opportunities within the cost action. How can we make sure that more people use those? And are there things that we can do to support and encourage young researchers to actually engage in these interdisciplinary collaborations? I have found that especially young researchers find it sometimes scary to get out of their comfort zone into interdisciplinary research. I kind of wonder if there's anything that we can do. Do our panel members maybe have any comments about that?
Maybe I can start. Maybe by having more summer schools or spring schools or whatever, so that they can put hands-on tutorials in specific subject, and to show the possible interdisciplinary actions they can tackle and get it further in their. So they have the freedom and the possibility to develop their own projects within these schools. So gives them more more courage to be able to consider these fields more seriously.
In a similar way, probably proposing we do that sometimes in the laboratory, because we have a big laboratory in astrophysics, but different subject, to promote wherever interdisciplinarity, you can do these PhD days, where basically just PhD students will present their subject, and most of the audience will be, of course, researchers and PhD, to show them how all these topics, even us, we see that there is a diverse, subject and question and everything, and probably making like an opening question, like a panel stuff, where we put basic question or questions that they need to tackle, and made them basically not doing like a hackathon like they do in coding and everything, but making them thinking how you could reach this solution, not making them working on it like for their life, but during a session, saying them, like you ask the question, what you want or what are your priority if you have enough money to do your research.
But it is really difficult for them to either conference or do the documentation to go to Europe. So maybe if you can hire someone that is works with this bureaucracy, then I can send you home safe. So they really have to be mobile, but it's very difficult to be mobile.
Just a sort of more costly one, to say that we have got these SDSM programs, so we've got money within the project to pay for short visits. I would encourage people to take a risk with them, because we've got a lot of them, so it's easy to do. So, for example, if there is somebody with a PhD student in astrochemistry who thinks maybe I'd like to do some DOT modeling of my molecules I don't really know and I've got first clue, come to Nottingham. They'll do it, spend 2-3 weeks with us, probably it'll be a complete waste of time not being a PhD, but you'll get your hands dirty and have a go at it and you'll break that interdisciplinary barrier, so it'll be worth doing anyway. So I think people should not hesitate to just get stuck in. If there's any students listening, go and shake your supervisors and say, I want to do this.
Yes.
Yes, so the one thing I would like to see happening in the action, and perhaps it is happening, but it's not very visible, are really discussions about going to the next stage in a larger collaboration with real funding for research, and thinking about putting together a proposal for doctoral training centres or something like that, where you really have the possibility to do these interdisciplinary collaborations, joint supervised PhDs. And I think that worked very well for the PAH community. That's why we have all these proponents of PAHs everywhere, because that was very, very successful. And I would like to see something like that happening. And maybe it is, I hope it is, but if it isn't, please start thinking about it. And there it's the younger members, the kind of, let's say, mid-range researchers who are the people who should really think about pushing that and get together to put something in for funding.
Okay, if there's no further comments, I think we've been doing this for an hour or something that's long enough, so I think we can wrap up there. So I would like to thank all the panelists. And I would like to thank all of you for your participation. So, and then I think Eleanor now.